So in the last video we have seen the pin diagram of the 555 timer and its two configurations, right? One a stable mode and the other one the monostable mode. So today we will see what is the functional block diagram. Okay, the functional block diagram of 555 timer. So what is meant by this functional block diagram? Since it is an IC, it consists of numerous numbers of active and passive components, right? So since we are not able to, it is unable to specify the complete diagram, the functional block diagram consists of those important components which are connected to the different various pins, that is from the first pin to the 8th pin. Okay, so we have to understand how to draw the functional block diagram. So the functional block diagram mainly consists of a string of 3 resistors. Okay, so string of 3 series resistors which forms a voltage divider circuit. So if this is your supply voltage VCC, now what is your VCC connected? VCC is connected to your 8th pin, right? So this will go on to your 8th pin. Okay, so the 3 resistors consist of the same value. Normally it is taken as 5 kilo ohm. Okay, 5 kilo ohm resistor, 5 kilo ohm. That's why you have the name as 555 timer. In the internal circuit you have 3 alike resistors, that is 5k resistors connected in series. Okay, so now you have to find out what is the potential across this point and the potential across this point. Okay, so if you want to find out the potential across this, it forms a voltage divider circuit, right? So how can we find out? So normally we have done for 2 resistors, right? So if this is your VCC and if this is your resistor R1, this is your resistor R2, what is the value of the potential at this point? If I take this as V2, what will be your V2 by means of voltage division rule? The total supply voltage VCC into what is the resistor across which you have to calculate. So R2 divided by total number of resistors, R1 plus R2. So if we apply the same condition with respect to the ground, in this case what will be if I take this as VA? Now what will be the potential VA? VA will be just similar to this, right? So VA, I can write it as the total supply voltage VCC into the resistor across this, right? So R divided by the total number of resistor, 1, 2, 3. You have 3 resistors. Now in this condition I am taking it as R. Okay, so R plus R plus R, which is equal to 3R. So what will be your value? VA will be equal to VCC into R divided by 3R. R will get cancelled, so VA will be equal to 1 by 3 VCC. Okay, so I have got this value. This is equal to 1 by 3 VCC. This is called as your lower threshold, lower triggering point, VLT. Okay, let me take it as VLT. So VLT is equal to 1 by 3 VCC. Now you have to see the potential across this. Okay, it is called as VHT, higher threshold, or you can take upper threshold, whatever. Let me take it as VHT. Now what will be this VHT? Now it is a potential with respect to the ground. So what will you get if I take this VLT, VLT, VLT? Now what will be your VHT? VHT that is your higher threshold will be equal to, again apply the voltage division rule, but whereas in this case it is a combination of 2 resistors, right? So the source voltage VCC into R plus R. So with respect to the ground you have to take both the resistor divided by total number of resistor, which is equal to 3R. So what will be your value? VCC into 2R divided by 3R. R get cancelled, so VHT will be equal to 2 by 3 VCC. Now you have got both the threshold values. So this will be equal to 2 by 3 VCC. Now you have got both the values. Next what you have is you have so a string of 3 resistors. The main components are a string of 3 resistors. So the first option is over, 3 resistors, and the second component is your 2 comparators, op-amp comparator, which compares both the values. Okay, comparator. So upper comparator and lower comparator. So how will you give the connection here? So this will be your upper comparator and here you will be having your lower comparator. Upper comparator, let me give it as UC, and lower comparator LC. Okay, so your higher threshold here, it will be negative terminal, positive terminal, here positive terminal, negative terminal. So your 2 by 3 VCC will be given to your negative terminal of your upper comparator. What will happen to your non-inverting terminal of your upper comparator? So we have seen in the pin diagram, right? Non-inverting terminal of your upper comparator, what will be connected? Your threshold 6th pin will be connected. So your non-inverting terminal will be going to your 6th pin, pin 6, which is nothing but equal to your threshold. Okay, so this will be VHT will be the reference for your upper comparator, one of the reference, and the other input is going to be your what? So this is your 2 by 3 VCC VHT. Okay, don't confuse. The second input is going to be your threshold. Okay. So from the same VHT, you are going to take the connection that is your 5th pin, that is pin 5. So this will be upper comparator will be having your 5th and 6th pin connection. So what is your pin 5? Pin 5 is nothing but your control voltage or your control pin, right? So control voltage. So upper comparator connection is over. So it will be having, one will be your 2 by 3 VCC, which is your upper threshold value, and your higher threshold value, and the other input non-inverting terminal will go to your 6th pin. So 5 and 6 will be given to your upper comparator. Now what is the next connection you have? What is happening? Your lower threshold point will be given to your 1 by 3 VCC will be given as the reference to the non-inverting terminal of your lower comparator, whereas what is happening to your inverting terminal we have seen in the pin diagram. So the inverting terminal of the lower comparator, what is given? The triggering pulse is given, right? Inverting terminal lower comparator, which resets the flip-flop. So you will be having from here, you will be having the trigger. So what is a trigger? Pin 2. Okay. So 2, 6, 5 is over. Now what is the third option you have? Both this output of the comparator will be given to as the input to your SR flip-flop. So this will be your SR flip-flop, which your output will be Q. Okay. So SR flip-flop and your output will be Q. So before that we have to know what is your SR flip-flop. So we know that the truth table of your SR flip-flop, okay, Q. So what are the combinations? 0, 0, 0, 1, 1, 0, 1, 1. Okay, so if S is equal to 0, Q will be equal to 0. If S is equal to 1, Q will be equal to 1. So 0, 0 means it is no change condition, and 1, 1 is your forbidden state or your race state, it is called as not used state, forbidden state. Okay, so now you are concentrating in only these two conditions when S is equal to 1 and S is equal to 0. Okay, so now set and reset. This is called as set and reset. So when S is equal to 1, Q is equal to 1. When S is equal to 0, Q is equal to 0. Or you can tell when R is equal to 1, Q will be equal to 0. In any way you can interpret it. Okay, so the third one will be your SR flip-flop. Okay, so flip-flop is over. Now this output of the flip-flop will be serving three different circuits. The output of the flip-flop will be serving as the input to a transistor, that is which is going to your discharge pin, NPN transistor, which will be given to the emitter will be grounded, and this will be given to your discharge pin, pin 7, right, which is called as discharge. Collector will be given to the pin 7, which is your discharge. Okay, so if Q is high, your transistor will be on. If Q is low, your transistor will be off. Now this will be again serving to the second state. So here it will be Q, here it is going to be a Q bar, because this is going to be the overall output. So the output is nothing but your inverting buffer. Inverting buffer. So if Q is equal to 1, your output will be 0. So it will be complement. Okay, so this will be your overall output, that is third pin, okay, which is nothing but your output. Okay, again the output of the flip-flop will be giving as it will be driven, or it will be driving one more transistor, that is called as a reset transistor, or it is PNP transistor. Okay, so this is going to be your fourth pin or your reset pin, where you will be having one more input, that will be your V reference. Okay, so this is your block diagram. So functional block diagram. So what will be your structure? This will be the internal structure of the inside the 555 timer, if I extend the ground here, so this will be your 555 timer internal structure. Okay, so this whole part is going to be your functional block diagram of your 555 timer, where all these points will be your pin numbers. So let us see once again what are the pin numbers. So here pin number 1, right, 1 will go to your ground, 1 is over. Okay, now 2 is one input which is going the trigger, 3 will be your output, 4 will be your reset, 5th pin and 6th pin will be going to your upper comparator, 7th pin is your discharge pin, 8th pin is your VCC. So these are the internal functional block diagram of your 555 timer. Now what is the working principle? So it has two triggering, the comparator, these two comparator mainly works on the reference value VHT and VLT. Let us take two cases now. In case 1, so let me take case 1, working principle. Case 1, what is happening? So when your non-inverting terminal, so your inverting terminal is given 2/3 VCC, right? When your non-inverting terminal, that is when the threshold is more than that of 2/3 VCC, when the non-inverting terminal of your upper comparator is greater than 2/3 VCC, what will happen to your op-amp? When your non-inverting terminal is more, now your value will become 1. Output of the op-amp will become 1. Now S will be equal to 1. When S is equal to 1, what will happen to your Q? Q will be equal to 1. When Q is equal to 1, the transistor will be on. Similarly, what will be your overall output? Overall output will be 0. If Q is 1, output is going to be 0. Okay. So this is what your first condition. Now what will be your second condition? So let me write it here. Case 1, non-inverting terminal of the upper comparator, if it is greater than 2/3 VCC, what will be happening? Your S will be equal to 1, which implies Q will be equal to 1. Set is 1 means Q will be equal to 1. So your overall output will be equal to, in the third pin, will be equal to 0. Okay. Now case 2. In the case 2, what is happening? See here, your next triggering point is 1/3 VCC. So when the inverting terminal of the lower comparator will be less than, right, will go below or will drop below 1/3 VCC, what will happen? Your lower comparator will get triggered and R will be equal to 1. So now here in the second case, when R is equal to 1, okay, when R is equal to 1, what will be happening to your, this is your first case. In the second case, when R is equal to 1, Q will be equal to 0. When Q is equal to 0, the transistor will be in the off. What will be your output? Output will change to 1. So it keeps on like zigzagging. It will be keeping on changing the position. R is equal to 1. Now Q will be equal to 0. Your overall output will be equal to 1. Okay. So this is how internally your comparator is working. Now when you connect the external components, as per we have seen in this diagram, it will be working as your astable multivibrator and monostable multivibrator. Okay. So the explanation of astable and monostable will be separately given in the next video.